Welcome back to our video modules on quantum mechanics. We're currently discussing the WKB approximation, and thus far we've looked at what happens if the potential profile is such that E is greater than V and such that E is less than V, and we've seen both sinusoidal and exponential responses from the wave equation with a fairly simple equation form if we make our assumptions that the frequency of the oscillations are much faster than the change in the potential. From there, we looked at tunneling, and we could see that we could calculate the transmissibility probability as a ratio of F over A with a couple slight modifications to the equation. Now, all that said, what we haven't looked at is what happens if E equals V. In this case, P is equal to the root of 2m E minus V, which means that the denominator when E is less than V and the denominator when E is greater than V both go to 0, which means we have an undefined solution to the equation. So how do we deal with this situation? Today, we'll be talking about the WKB patch and the strategy for how it basically works. Well, let's clean this up a little bit and see what we can do. Please note that the shown forms of the wave equation only include the negative exponential forms. The full solution includes both positive and negative forms. Now, what I've done here is I've recreated the potential profile that we used when we were calculating our tunneling transmissibility. And we can see that we have two areas of concern where E equals V, right here and right here. A good way to approach this is to separate this graph into regions. Proceeding from the left, we'll say region 1, this is a sinusoidal function. We know that the wave function is operating sinusoidally. Region 2 will be where E is very close to V or equal to it. Region 3 is where we have some sort of exponential decay. Region 4 is where, once again, E is very close to V. And then finally in region 5, we're going to return to some sort of sinusoidal type wave function. Now 1, 3, and 5, we already know how to handle. What we need for region 2 is something that has a little bit of sine and cosine and a little bit of an exponential function. And in fact, a function like this exists. They're called the Airy functions, and they offer solutions for equations of this form. And if one were to graph these Airy functions, they would look something like this. There's actually two versions of the Airy function. One leads to an exponential increase, the other leads to an exponential decay. So mathematically, if we were to take a look at region B and we assumed that right in that region, right at B, V is linear, and we make a quick substitution where Z is alpha x, and a quick note that anytime you use the substitution Z equals alpha x, make sure that the origin of your x coordinate system and the origin of your Z coordinate system line up, where alpha equals 2m over h bar squared times v prime at 0 to the 1/3 power, we can actually reduce Schrodinger's equation to this right here. Now let's zoom in on B and see if we can figure out what's happening here. Now we know to the left, where E is definitely less than V, we have some sort of exponential. And we know that far to the right, where E is much greater than V, we have some sort of sinusoidal function. Therefore, our area of concern is going to be right here. And we know that the Airy function is going to describe the behavior of the wave function in this region. So with that little introduction, I'm going to call this video a wrap, as we see that the Airy equation provides a solution for the wave function when E is close than V, in other words, where the WKB approximation fails. Join me in our next video as we explore more of the details of how we use the Airy function to approximate the full behavior of the wave function. I'll see you then.